DfM, and we decided to redesign the hand winch for manufacturing. My name is Emma, and my teammates are Jennifer, Maddie, Cameron, Lucas, and Nashir. So a winch is a mechanical device to pull or lift heavy loads. A hand crank rotates a drum which is wrapped up with a rope, a cable, or a chain, and as this is turned, it turns a gear chain that causes the drum to rotate and tighten or loosen the rope, cable, or chain wrapped around itself. This allows for a mechanical advantage by using the hand crank and allows people to lift heavier loads they might not be able to without this tool. So the estimated annual production volume is 75,000 units a year. The current market size for winches is $1.74 billion, with $0.24 billion being for primary customer owners, your private boat and trailer owners, and $1.48 billion for electrical winches used by agricultural and marine businesses. This is the CAD model of our winch design. Looking at our function diagram, we knew that the most critical function was to lift loads, and then we split those up into different functions so that we were not compromising any of the essential functions when redesigning our part. Looking at this chart, we wanted to make sure that we were looking at parts that had a high manufacturing assembly cost and also high functional importance. That way our redesign would have the most benefit. We looked at the spindle shaft, platter, and gears. Looking at the functions for each subassembly, we wanted those subassemblies that, again, had the most functions in order to maximize our effort. So the crank arm assembly included 4 essential functions, whereas the base and the low-speed shaft assembly each included 2. So we look at these specific assemblies for redesign. For both customer groups, we have these core functions, but things that might be different would be creating torque and guiding rotation, since that changes depending on the application. Again, these are things that are in common for both groups. However, a boat owner might not need a low gear assembly if they're not lifting heavier loads. And the crank arm assembly is also not needed in an electrical variant. These are our 2 variants of our product, the difference being the electric motor instead of the hand crank. These are the 2 module interfaces for both of those variants. And then looking at these 2 variants, we wanted to delay product differentiation in order to optimize the manufacturing.
Here's our design for manual assembly. We've chosen first our spindle insertion step. On the left here, you can see all the parts for this associated step, and highlighted in yellow are the parts with the highest amount of assembly time. The quad chart classification. Highlighted in yellow are all the parts that we feel best candidates for DfM. All the 4 parts that we showed on the previous slide are highlighted here, as well as an extra part, the spindle sleeve, which has both a low functional importance and low cost. Insertion step after DfM. So we reduce the number of parts by getting rid of the second spindle plate that's attached to the big gear, and also combine the spindle sleeve and spindle shaft together. We've also reduced the number of fasteners by getting rid of that second plate, remove the need for the rivets to attach to the big gear, and also chose to do press fits instead of welds to reduce the assembly time. We've also reduced the part variety by using circlips instead of an N12 bolt and nut to constrain the axle, and also provide a locating feature for our cable clamp by adding a small divot onto the spindle platter for better alignment for our cable clamp.
Now we'll see design for manual assembly for the module low speed shaft assembly. We took small gear and low speed shaft sub-assembly and applied some design changes to increase efficiency. If you'll see, before we had 3 components: low speed shaft, its sleeve, and a small gear, and the highest assembly time was of 13.13 seconds for the small gear which was getting welded onto the shaft. Post our DFA, we just got 1 body, and that was a low speed shaft gear with a reduced assembly time of 7.13 seconds and an efficiency boost of 27% from the previous value. As we can see in the quad chart classification, speed shafts and gears are having high functional importance with low and high cost respectively. This is the previous iteration where the gear was getting welded onto the shaft, whereas the new one in which the gear is present on the shaft during machining itself. The design guidelines that were followed are DFA1, reduced part count. We combined shaft sleeve, small gear and shaft together, and we decided to put gear on shaft during machining itself so as to reduce 1 step of welding. DFA4, allow hand and tool access. New assembly didn't need any extra process such as welding, so it became pretty easy to fix it by hand, allowing a smooth movement of hands and tool on the winch's base. Next up was DFA6, which was increased part geometry. To make it more symmetrical so as to get alpha and beta values under 180 degrees, to make it more easy for assembly, we put gear right in the middle of the shaft. All of this led to an assembly time of just 210.35 seconds, an increase of 55.75 seconds or about a minute.
When choosing a subsystem to optimize for automated assembly, we found the crank arm was a strong choice. The significance of the three components that make up this subsystem are shown below in our quad chart classification. These components include an arm crank, a handle, and a handle sleeve. Here's our design before and after its optimization for automatic assembly. Three of the major design changes included are an added lift to the crank arm, as well as a threaded end to the handle, as well as raised lips on the handle. These design changes were made in accordance with DFA 7, 3, and 11 respectively. Changes resulted in an assembly cost 96 cheaper than original.
For redesign is the handle sleeve. The critical dimensions are 90 millimeters in length, 26 millimeters in diameter, and 16.5 millimeters in internal radius. Important because the user must grab onto the handle to create torque, and it must slide onto the handle shaft. The material is a thermoplastic, the shape is circular, the mass is 28 grams, the section thickness is 6.5 millimeters thick, the tolerance is plus or minus 0.5 millimeters, the surface roughness is 0.5 micrometers, and the production volume is 75,000 units. These meet the requirements for injection molding. Here is the handle sleeve. The total cost per part is $2.52. The handle sleeve are the following. 1. Reducing part thickness. 2. Having a uniform wall thickness throughout the entire length. 3. Adding a 5-degree draft angle to the end. 4. Eliminating one side pole by eliminating a rear chamfer. After DFM, here is the handle sleeve. Were saved per part, leading to a total cost per part of $1.76. This is mainly due to the reduction of one side pole and therefore a lower bolt cost. Here are the critical dimensions after DFM.
The next component we looked into redesigning for manufacturability was the spindle platter. The purpose of this sub-assembly is just to increase torque, so the tolerance is plus or minus half a millimeter to not impact torque. Based on the material, shape, mass, etc., we narrowed the process down to sheet forming and machining, and selected sheet forming on account of it being cheaper. This is the spindle platter following DFA. Through analytical analysis, we found the material cost to be 75 cents, operator cost to be 28 cents, mold cost to be 14 cents, and the total cost to be about $1.17. Based on the results from DFM Pro and DFSM 8, I increased the distance between the holes so they weren't too close. Following DFSM 5, I changed the holes to be 20 millimeters, a standard size. Finally, based on DFSM 8, I increased the fillet radius to be the thickness of the part to avoid sharp bends. This modified part had a material cost of 75 cents, operator cost of 28 cents, mold cost of 15 cents, and the total cost was about $1.17. The cost of the original modified designs was found to be about the same through analytical estimation. Using Hubs.com, both the original and modified parts were quite a bit more expensive, likely due to very long-range extrapolation, and in this estimation, the modified part was quite a bit cheaper than the original part. The CAD of this redesigned spindle platter can be seen on the right.
When looking at a product service system for this device, we looked at including installation, maintenance service, insurance, and how-to manuals. This would ease installation and use of the product and optimize the customer experience. Would only pay once for all of these services, and it would prevent non-functional parts from just going for the landfill or the customer having to buy a new product. For the design for assembling manually, the platform reduced down to 34 cents per part, and the small gear subassembly reduced down to 3 cents per part. Then we would probably recommend the platform instead of the small gear subassembly. For the automated design for assembly, automation improvements came down to 83 cents per part. We would recommend implementing these changes. For design for manufacturing, the handle came down to 76 cents per part, and the spindle plate 0.02 cents per part analytically and 0.45 parts. Design did reduce price and simplify our design. Here are some things we would do differently. We would change the base to be a simpler shape without the lip so it's more easily manufacturable. We would make the spindle platter flatter and more easily manufacturable without sacrificing function, and we would do design for manufacturing and assembly so that we can optimize our design. Thank you for listening.